Hi, this is a lecture giving you an overview of the t-test statistic. We'll be focusing on one sample t analyses for this lecture, and there'll be subsequent lectures on independent samples t and dependent samples t, so we couldn't do it all in one. So let's get into it. First we need to go over the assumptions of Z. One is that the sample mean approximates the population mean, or the mu in this case for population mean. This is basically law of large numbers, that the larger n you have, the more likely the sample mean is going to approximate the population mean. And then we have that an assumption also is that SE indicates how a mean approximates a mu. So basically your standard error indicates how well your sample mean approximates a population mean. So remember those two assumptions. So what are some problems with z-scores? Requires population standard deviation. We don't always know that. You know, we can make an estimate of it, but sometimes that value is unknown. That makes it difficult to calculate standard error if you don't know your actual population standard deviation. And the fact is, as I just said, we usually don't have this. You know, there's many situations where we can't approximate it very well because we don't actually know the population standard deviation. So, ergo, we must estimate the standard error from sample data. So we end up using the standard error from sample data, but that's not a reflection of the population necessarily. So, estimated standard error. It's basically standard error estimated from the sample, and it's denoted as S sub m, or the sample standard error of m. The formula is as follows. Estimated standard error is S sub n, and whenever I say sub, that refers to subscript, so S sub m equals S, which is standard deviation, over square root of n. Or you can conversely write S squared, which is variance, over n square root over that whole function. Now we introduce t. T is z's cousin that can make handling situations where population standard deviation is unknown more palatable. So if you don't know your population standard deviation, which is, well, a lot of situations where you don't know this, you need to use a t. So when do you use a t? When you can't use a z because you don't know the population standard deviation. So the formula is very much the same. It's very similar. It's m minus mu over estimated standard error. So really only the denominator function changes, and you have an estimated standard error because you don't know your population standard deviation. So you're actually going to end up using t more than you use z, because it's hard to know what your population standard deviation is in most cases. And so what's this? It's the estimated standard deviation, standard error, sorry. So S sub n is the estimated standard error. Okay, so degrees of freedom, again, but just making sure to reiterate, describes a number of scores that are free to vary. So your degrees of freedom are the number of scores that are free to vary. And one sample t-test statistic is the degrees of freedom, or df, equals m minus 1. Why is that? Basically, it's because you are estimating a population parameter that you do not have, and that is the standard deviation. And you're estimating it by calculating an estimated standard error over the standard population standard deviation. So you've lost 1 degree of freedom there by doing that. So n minus 1 equals degrees of freedom. Now, depending upon the statistical analysis you use or choose to engage in, the degrees of freedom calculation will vary. So n minus 1 is not always true. So for instance, when you're doing an independent samples t, you're actually going to do n minus 2, and we'll get into that later. But for a one sample t-test statistic value, the degrees of freedom is n minus 1. Okay? And we calculate a sample standard deviation to replace the estimated standard error or in the calculation of the estimated standard error, and we'll get into that in a second. So what is the shape of t? The t distribution looks like a z distribution mostly. It's pretty close. The t distribution is more shallow, and why? And why would that be? Basically, it's because, I'll give you a moment to think about it, but basically it's because the mean is approximating the mu according to the law of large numbers, but the t usually doesn't have the same sample size, so you don't always approximate it as well. And the other issue is that degrees of freedom. You have one less degrees of freedom. And remember why you have one less degrees of freedom? It's because you are estimating the standard error in the denominator versus knowing the population standard deviation. Okay, hope that makes sense. So you'll see the normal distribution, which is the z distribution, where population mean and standard deviation are known. It's an ideal situation that doesn't always occur. And then you have the t distribution, where df equals n minus 1, and in this case 20. So that means your overall n was 21. If degrees of freedom is n minus 1, then your overall n for your sample was 21. And you see how that more likely approximate the normal distribution, because as the larger n you have, this goes back to the law of large numbers. The larger your n, you're more able for your sample mean to approximate the population. So larger is always better when you come to the law of large numbers. And then you look at the t distribution for degrees of freedom of 5. If you have a degrees of freedom of 5, that means you have an overall sample size, in that case, of 6 for one sample t, because degrees of freedom, again, is n minus 1. Okay, and you see how that's more shallow? Because you're less able to approximate the population mean and the population distribution because you have a smaller sample. So this all goes back to the law of large numbers. Okay. Given that t and z are different, they're different distributions, you have new critical values. Please refer to a t-score table. There's definitely one in your book, but if you're ever without your book, you can just Google t-score table or t-table, and there are a gazillion out there, and same thing with z. And almost all the tables you can find multiple versions. So what does a hypothesis test look like? With the t, pretty much the same logic with the z or any kind of hypothesis testing. There's a new calculation in the denominator with the sample standard deviation, where you're estimating that standard error, and new chart with degrees of freedom. So hypo testing with t, or hypothesis testing with t. Let's look at an example. First, the premise of this example is that animals avoid direct eye contact. And we have 9 birds that are sampled. And they're allowed to roam freely in a box with 2 chambers for 60 minutes. And this is what the box looks like. One side of the box has googly eyes, and so this is so that animals, and then the other side of the box, which you can't see, doesn't have any googly eyes. And what's implied, or what the hypothesis is that the birds, the researcher thinks, is that the birds are going to avoid the googly eyes. They're going to avoid that direct eye contact, and they're going to spend more time on the other side of the box. So the null hypothesis, or the hypothesis that nothing is going on, would be H sub O, subscript O, that mu on the plain side, meaning no googly eyes, is going to be 30 minutes. So basically that they're going to spend equal time on each side of the box. So alternatively stated, the alternative hypothesis would be mu sub plain side does not equal 30 minutes. So there's going to be some difference. And that's really the researcher's hypothesis. The researcher thinks that the birds are going to avoid the direct eye contact. So they're going to, it's not going to be an equal 30-30 on each side. And there's actually going to be more time on the plain side. So is this a directional or non-directional test? Well, based upon the hypotheses that we just outlined, it is a non-directional test as it's stated right now. What should you set your alpha level at? 0.05 is kind of standard, but you can also use 0.01. Where's the boundary for my critical value? You would find that in your t-test chart. And how do you find that? First you find out what's your DF, and you know what your N is. Your N is 9. So 9 minus 1 is 8. So your DF is 8. Second, you look up the t-value based upon whether it's one directional or non-directional. In this case, it's non-directional. And the alpha level, which is 0.05 or 0.01 depending on the context. So we calculate our t. Remember, t-test uses sample calculation of variance and standard deviation. So our standard deviation is s squared equals sums of squares over n minus 1, or conversely, sums of square over degrees of freedom. In this case, the sums of square value was 288 divided by 8, and they got the 8 as the degrees of freedom because you have a sample of 9 birds, so n minus 1 would be 8. So 288 divided by 8 is 36. Then you take your sample standard deviation to estimate standard error, so you can fill in the denominator portion of your t-test calculation. So standard deviation squared, which is variance, over n square root will give you your estimated standard error. In this case, your variance is 36 divided by 9. Square root equals square root of 4, which equals 2. So your estimated standard error in this case is 2. Our t-test statistic equals t, which equals t equals m minus mu over estimated standard error. Our mean in this case was 36 minus 30 over 2, which gives a resultant t-value of 3. A t-value of 3 is pretty high, so I'm going to say we are rejecting the null. I haven't looked at the t-test, the t-chart value, but I would be inclined to say yes. So what are some assumptions of t? Values must be independent. That's pretty much much of parametric statistics. Values must be independent, or observations must be independent of each other. Values must be normally distributed, so a normal distribution. And both of these assumptions are the same as z. Now what's the difference between a t and a z? That's right, population standard deviation is unknown for a t. So you have to use a t and estimate the standard error based upon the sample standard deviation. So measuring effect size, how do we do that? We can calculate a Cohen's d as before, so estimated d equals the mean difference over sample standard deviation. So notice that this is very simple it's very similar to the t calculation, but for the denominator it's just the plain Jane standard deviation, not the estimated standard error. So remind yourself, sample SD, sample standard deviation here. So given your eye spot example with the googly eyes, you can calculate your Cohen's d value because you have the numbers already. So actually calculating your Cohen's d after you do your t-test is actually quite simple. So we can calculate as follows for the sample. So the mean difference was 6 over sample standard deviation of 6 equals 1. That's actually a quite large value of Cohen's d. So is it a small value? No. The general metric for Cohen's d is 0.2 is small, 0.4 is medium, 0.5 is medium, and anything above 0.8 is large. So variance explained. That's another way of thinking of effect size. Cohen's d is popular, but there are other measures of effect size. R squared is another measure of effect size, and it indicates the amount of variance explained in the dependent variable by the independent variable. So for formula for R squared is the t-value that you calculate, not from the chart, the t-value that you calculate over t-value squared over t squared plus degrees of freedom equals R squared. So please note, t is your test statistic, not the t critical value. So R squared we can calculate from the example as 3 squared over 3 squared plus 8 equals 9 over 17, which equals 0.5294. That's quite high. That's saying that approximately 52.94% of the difference in the DV, dependent variable, is explained for by the IV. So in the googly eye example, you would say something like 52.94% of variance and time spent on either side of the googly eye box, plain side or googly eye box side, is explained for, that time is explained for by, or is explained by the presence of googly eyes or not. So how do we interpret R squared in general? Percentage of variance explained. So an R squared value of 0.01 is considered a small effect, while R squared equaling 0.09 is considered a medium effect, and R squared 0.25 is a large effect. Now our colleagues in the hard sciences look at those values and think that's pretty small. If you're thrilled with like 25% of the variance explained, really? Are you really thrilled about that? And like, yes, because we're dealing with human beings and birds and animals and, well, mostly human beings in education. And human beings are not as predictable as some of the more hard science concepts like material testing or whatever in engineering. So our standards are different for the social sciences versus hard sciences. Sample size and variance. Given the equation for t, which we, just to review, it's t equals m minus mu over estimated standard error, where estimated standard error equals the square root of variance over n, or otherwise stated as standard deviation over n. What do you think happens when sample size increases? When sample size increases, what happens? What do you think happens when variance increases? Okay, so when sample size increases, basically you're more likely to reject your null hypothesis. And that's because the estimation of your estimated standard error gets small. And this leads directly into the second question. What do you think happens where variance increases? Now, if variance increases, you're more likely not to reject your null because your denominator becomes, your estimation of your standard error becomes larger. So you're more likely to get a lower t-value in the calculation. So there's this relationship you need to be cognizant of. So directional t-tests. Directional, or otherwise known as one-tailed t-tests, are pretty much the same as one-tailed z-tests. First, we state our hypotheses, going back to the googly eye box example. So H sub O is mu sub plane side is less than or equal to 30 minutes. So not more than half of the hour on the plane side. And our researcher hypothesis would be that mu sub plane side is greater than 30 minutes. So basically that we think as researchers that the birds are going to spend more time on the plane side of the box, trying to avoid that direct eye contact with the googly eyes. We're going to locate the critical region. So given n equals 8, alpha of 0.05, and this is a one-tailed test, we can find a new boundary for our critical region. We have to know what our degrees of freedom are. So what our degrees of freedom in this case is still n minus 1 because it's still one sample t. So n minus 1 equals 7. And then we have a one-tailed test, and then the alpha is 0.05. Then we can calculate our t-test statistic, which we already know is 3.0 from our previous calculation of it in the one non-directional test. So as you can see, regardless of whether it's a non-directional or directional test, your actual t calculation, the t statistic that you calculate, will stay the same. It's the t critical value that you look up in the chart that's going to change. So now we can make a decision. Do we reject or null? I would say you're even more likely to reject your null in this case because you're implying a directionality to it. So, and that was the presentation on one sample T. Next week will be, or next lecture will be, the independent samples T. Thanks.